So I'm happy to give this talk. I wish it could have been in India. I've never been to India, so hopefully in the future I'll get a chance to come. So I'd like to thank my collaborators, Eduardo Grossi, Alexander Soloviev, who will talk next, and Fanglita Yan, and my other collaborator who's not on this work but related works is Juan Torres. Okay. Now, okay, so here's just a few introduction slides. I mostly care about heavy ion collisions. Here's a picture of a heavy ion collisions. You have two nuclei, they collide, they go splat, they spew out a spray of particles which fly off to the detectors, roughly 20,000 or so. And those 20,000 particles seem to obey hydrodynamics, not seem to, I mean, the evidence is overwhelming, okay? And just if you, these days we have such great data, you can just plot the energy flow in the calorimeter and you can see the hydrodynamic with your own naked eye, okay? So here's a plot of the energy flow in a heavy ion collision. So here the two nuclei collided head on, not exactly head on, they had a almond-shaped overlap and there was energy flow going this way, and this is what they see in the detector on the CMS detector. You see beautiful elliptic flow here of energy flying off one way or the other. So for some number of high energy experimentalists, seeing is believing, and when they saw this, they started believing in hydrodynamics. Okay, so let's talk about the trajectory of a heavy ion collision in the phase diagram. So here's this basic picture. We start out at high temperature. We sail along the T equal mu equals 0 axis, and we fly through a region with chirally restored, and then chiral symmetry breaks, and we have, in the vacuum, we have broken chiral symmetry. And chiral symmetry, although it's prominent here, actually plays no role in sort of current understanding of heavy ion data. It sort of, except through the equation of state, very tangentially, essentially this fact that you have Q bar Q that goes from 0 to non-zero doesn't enter in the description at all, okay? And so the evidence for chiral symmetry breaking or this chiral phase transition is non-existent, okay? So I'm going to try and work on that a little bit in this talk, right? Sort of say, what is the role of chiral symmetry breaking, how to incorporate it into hydrodynamics, and so forth. All right, so I'm going to first talk about this region of broken chiral symmetry. Okay. Oh, sorry. So although it plays no role in the heavy ion collisions and simulating heavy ion collisions, it is seen on the lattice. Okay, so this is one slide to try and show you the role of chiral symmetry in real lattice QCD. Okay, so what they're plotting here is the susceptibility, what they call chi-m. It's the second derivative of the partition function with respect to the quark mass. Okay, and so basically, if you were close to an O4 critical point, which is where of chiral symmetry, then you would expect very definite scaling predictions for how this chi-m should depend on temperature and quark mass, okay? So here's the basic prediction. You would expect this chi-m to go to like m quark to some critical exponents, and then you would have a scaling function. The scaling function is a function of this parameter usually called z, which is a function of the temperature and the quark mass, again, with known critical exponents. And a lot of what's seen in the real lattice data is that a lot of the trends of this chi-m, right, are reproduced, or at least qualitatively reproduced by this O4 scaling function. Okay, so here's just what I'm plotting here is this is chi-m for different values of the quark mass, okay, the light quark mass. So the physical point is right here on this green line, okay, these green points, okay, and then they actually go below the physical point. So we reduce the quark mass from its physical point down to a Pion mass finally of 55 MeV, okay? And basically these trends that you see in these curves, in particular this flows of these lines, the position of the peak as a function of quark mass, is rough, can be made sharper, but basically following the predictions of this O4 scaling model. So I would say the lattice has provided some good evidence that, real world QCD somehow knows about this O4 critical point, and yet it plays no role in our heavy ion collisions, right? So we should try and find evidence for this whole O4 critical point that they see in the lattice in the heavy ion data. So, so let's talk about hydrodynamics with broken chiral symmetry. And here I'm following Son and Stefanov. So if you had, and we're talking here about the strict chiral limit first, okay? So in the strict chiral limit, you have some conserved quantities. You have the stress tensor, the baryon number, the isovector current, okay, and the isoaxial vector current, okay. And maybe the most important thing would be to say that every time you see a hat, okay, it means the conserved, it means axial, okay. So this is, hat means axial. So this is the isovector axial current that is conserved in the limit that the quark mass is 0, okay. Now, if the symmetry is broken, then you have to include, so it's, you have to include the phases of the chiral condensate into the hydrodynamic description. So if the symmetry is broken, there will be a Goldstone mode, which is, we call the Pion. That Pion can be arbitrarily long wavelength, okay? And will live an arbitrarily long period of time as the wave number goes to 0, okay? And so you need, that being said, you need to incorporate these Goldstone modes into the hydrodynamic field, just like you do the chemical potential, the temperature, the flow velocity, and so forth, okay? So, and the Pion field, to be strict about it, is the phase of the chiral condensate. Okay, so we're going to write down, or Son wrote down, this theory of the hydrodynamics with this Goldstone boson, and then some generalization by us would be to then include a mass term, so the Goldstone boson fields decay at large distances, okay, which is more the physical world. Okay, so here's the basic picture, right? So mass is very, very small, okay? You have the temperature, which is whatever it is, of order lambda QCD. You have the Pion mass, which is much less than pi times the temperature. And then you have very long wavelengths, which are even less than the Pion mass, okay? So for very long wavelengths less than the Pion mass, then the Pion doesn't contribute. You just have ordinary hydrodynamics that we are using and love, okay? For modes with momentum of order the Pion mass, then you need to include the Pion as an additional hydrodynamic degrees of freedom, okay? And I will call those the superfluid modes, okay? And then for very short wavelengths, of course, then you start seeing the microscopic particles in the hadron gas, okay? So for momenta of order 3t, you start seeing this. So maybe a question that might come up is, do this scale separation exist in practice? It's borderline, okay? So basically, if you ask about the typical momentum of the particles running around, okay, that's like 600 MeV, okay? The Pion mass is 140 MeV. So it is so to say small compared to the typical momentum. And even more so when you consider that the effects usually come squared. So the Pion mass squared over pi t squared is a pretty small number, providing a useful expansion parameter. Indeed, if you look at the heavy ion data, very rarely do they plot momentum of order the Pion mass, right? That's typically too low for them to measure, though they can do it. Right, so now the question is going to be asking, how does this intermediate modes contribute to the pressure and the shear viscosities and diffusion rates of the long wavelength theory, which is ordinary hydro? Okay, and so that we're going to use the superfluid theory and we're going to work that out, okay, how these superfluid modes change these transport coefficients of real QCD. And you get an expansion in terms of the Pion mass, okay? And roughly speaking, well, not roughly, it's going to look something like this. So we're going to show that the transport parameters have been following expansions in the around the MQ equals 0 limit, the chiral limit. The bulk viscosity is some bulk viscosity in the chiral limit minus the term which goes like linear in the Pion mass. The shear viscosity goes like same thing minus a term which is linear in the Pion mass. Okay, and the isovector conductivity goes like 1 over the Pion mass, and as we'll discuss. Okay, so from a mathematical perspective, right? If you ask how does these terms are non-analytic in the quark mass, right? So the Pion mass goes like the square root of the quark mass, and so from a mathematical perspective, these are very similar to long time tails. You have sort of non-analyticity here, okay, in the quark mass. And as such, the calculation will be very similar to sort of hydrodynamic loops and the calculation of long time tails. All right. So let's just talk now first the pressure, equilibrium pressure. So this may be known to a fair number of people how to do this. Okay, so if you have some soft modes, then if you start writing down the Euclidean partition functions, you would like first integrate out all the hard modes, which have non-zero Matsumbara numbers, and then you would be left with an effective Lagrangians for soft modes with and p of order m pi, not m pi t, p of order m pi, no t, sorry. And you would write down some effective Lagrangian for your Euclidean partition function, which would have to respect the symmetries of the problem. And then it would look like chiral Lagrangian in 3 dimensions. So you would write down an effective 3-dimensional Lagrangian for your Euclidean partition function, which would have some derivative couplings to the phase of the chiral condensate. And if you have a mass term, you would add a mass term. Okay. So for the most part, and the parameters here, f squared of t and m squared of t, those are functions of temperature and are just matching parameters that you would need to match. Okay. So for small Pion field phase phi, you just get a simple quadratic Lagrangian in the phase angle phi, and you can do this integral, right, Gaussian, and you get a correction that describes the contribution from soft pions. Okay, so you get some piece which is analytic in MQ, and then you have some correction coming from these soft pions. Okay, now, so for most of my talk, I mean, what's also important is that near the critical point, the O4 critical point, these parameters have a universal behavior, okay, and which is known, okay. So in particular, you know that this f squared m squared, that's like the chiral condensate. It scales with some known critical behavior like MQ times T reduced temperature to the power beta, okay, with known critical exponents. And similarly, this is related to the correlation length, and it also has a known critical behavior near the O4 critical point. From another perspective, all of those, it's Euclidean, so both this parameter f squared and m squared can be computed with high precision in real world lattice QCD. I would say that m squared has already been computed with high precision, and f squared still you could work on a bit. Okay, good. So once you have the pressure, right, this is essentially the pressure, then sort of standard technique tells you what is ideal hydrodynamics, right? So of course, this was probably known to Landau and other people, but in the modern world, we would say this serves as an action for the hydrodynamics. Write down the action. And then by varying the action, you can find with respect to the metric, you can find the stress tensor corresponding to this hydrodynamic theory. And by varying the action with respect to the gauge field, you get the current associated with the theory. So what you see is basically a kind of piece that looks like hydrodynamics that we love, and then you have this superfluid stress, which adds some extra terms, kind of like a minimally coupled scalar coupled to the rest of this stuff, okay? And also the current has a normal piece, normal fluid, and a superfluid piece, which is coming from this derivative of the phase. Okay, now finally, in an extension of the formalism, you have another constraint here, which relates the time derivative of the phase to the chemical potential, and that's known as the Josephson constraint. Okay. So essentially, the Josephson constraint comes from requiring that this psi bar psi operator commutes with the grand sum. Otherwise, it wouldn't be stable in time. Okay. Now, if you have a mass term, you get some corrections here. And in particular, the current is not exactly conserved, but is only partially conserved. And so you get some corrections to the non-conservation, which is known as partial conservation of axial current. Okay. Now, so that's ideal hydro, great. And so then you go on and you start calculating higher derivatives, which are viscous corrections. I should say that, we want to, well, let's go on. Let's calculate higher derivatives. So this is work by Son and Stefanov and a bit from us, and I'll say what the bit from us was. Okay, so you have this partial conservation of axial current together with this Josephson constraint, and now we're going to add dissipative corrections. So the current you write as some ideal piece, superfluid piece, and now you would add a dissipative correction, and the first term that you could have would be like an axial conductivity. Then of course you would need to add noise if you in this theory. Okay. Now the Josephson constraint would also get corrections, so the time derivative phase would not be exactly mu, but would have some viscous corrections. And the two terms that you can write down by tensor and counting and so forth would be one, which is a gradient of phi squared, and since the mass is a parameter too, you could also include another term which goes like m squared phi. Okay, just some damping rate. Okay, so this says dt d phi is m squared phi, just a simple damping rate. So now kind of the bit from us, well, first of all, they worked with the linearized analysis and we made it nonlinear. And then the bit from us was to analyze the constraints that entropy production should be positive, okay? And that led to a reduction of coefficients. And it turns out that there's only, instead of two coefficients, there's actually only one coefficient there if you're going to require that entropy production be positive. So the whole theory is sort of determined by sort of two coefficients, two dissipative coefficients. One is the axial conductivity, and one, I don't know what to call it. We were calling it zeta 2. Okay, good. So finally, if you're going to reach equilibrium, then the fluctuation dissipation theorem fixes the strength of these noises. And in particular, the strength of this current correlator is 2t sigma, and the strength of this noise correlator, phase correlator, is 2t zeta 2. All right, so now that we have kind of the equation of motion here written down, let's analyze the dispersion curve of the excitations that arise. Okay, and that's what we did here. So again, this is really Son and Stefanov's work. So we linearized the equation of motion, try and find the dispersion curve. So one finds that the wave has a dispersion curve, minus I omega q times I gamma. And just to record here what these parameters are, so omega q is this quantity, right? So it looks like a normal dispersion curve, except it has this extra V naught squared sitting, okay? and V naught squared is this ratio of quantities and somehow called the Pion velocity. Okay, and in particular, if you had m equals 0 in the chiral limit, this would just be, that's where the omega would just be VQ. Okay, so the damping rate, this gamma, is determined by our two coefficients, sigma and zeta 2, and I parameterize it here. So the damping rate of the Pion field is parameterized by two numbers at small momentum, one of which I call dA, okay? It's proportional to q squared. And the second of which I call dm, and it's proportional to m squared, right? So because you have a mass, the Pion field can just decrease in time at zero momentum, and that's what this dm records. Okay, so I would like to spend just a second here to talk about this Pion velocity, because it's important and its meaning is important. So if you look at the ideal massless Pion equation of motion, so chiral limit, then you have a conservation of axial charge, and it looks just like a minimally coupled scalar equation. You have here kind of conservation of axial charge. Axial charge is this derivative, time derivative of phi, and you have the current, which is this spatial derivative of the phase phi. Okay, and now if I look at this axial charge piece, right, it would be typical to break it up. This is the total axial charge. It would be typical to break it up into what's called the supercomponent, which has the same coefficient, f squared time derivative of phi, and a normal component, which would be some additional piece because the charge doesn't have to be just the supercomponent, right? It's that normal component. So the Pion velocity, right, is, yeah, it's f squared over chi, and it's sort of say, you can see that it's the ratio of the supercomponent divided by the super plus normal components, right? And that being said, near TC, like this normal, the super component becomes 0 and the normal component becomes dominant. And so you basically get an expectation that near TC, the Pion velocity should go to 0. Okay. And we'll try to think about that a little bit. So now coming back, we have written down the theory of our stochastic superfluid, and we want to compute their contributions to the transport coefficients. And so what do, right? So you have a theory, you drive the system with some gravity to drive it out of equilibrium. Then, these modes will be driven out of equilibrium, the hard modes. The superfluid modes will be driven out of equilibrium. And at long wavelengths, you'll have these hydrodynamic contributions. And what you want to do is integrate out these superfluid modes and calculate their effect on the dissipation at long distances, right? So one way to do it, right, would be just to write down a hydrodynamic loop for these superfluid modes, and that's what I tried to show here, and that's probably the most expedient way to do it. Okay. Alternatively, and this is the approach that I will adopt here, is you could write down a kinetic equation for these superfluid modes. So I will basically do that for this stochastic hydrodynamic system. If you have a separation of scales, which we do here, I mean, these wavelengths are much shorter than these black light wavelengths. You can write down kinetic description of these modes. All right, so let's do that. We're going to develop a phase-space description for these hydrodynamic modes. Okay, so essentially, this is kind of a framework. Well, this has been discussed a lot. Basically hydro-kinetics that come from these superfluid modes. And here it's sort of an extension of that. Basically, you evolve the linearized equations of superfluid hydro. The stochastic equations of motion take a simple form. They're kind of like matrix versions of Brownian motion. Okay, so you sort of have ideal piece, some dissipative piece, and some noise pieces. And then you would break this matrix system up into eigenvalues and eigenmodes. And of course, you get what you expect, right? The eigenmodes have this dispersion curve, okay? That the omega k is this plus minus v squared plus k squared plus m squared. Okay, now you want to analyze the 2-point functions in order to determine how the phase space density evolves, right? So what you do is you take the Wigner transform of the 2-point functions, okay? And that would be interpreted as the phase space density of these Pion fields. Okay, so making this Wigner transform, you get what I call W++. You have the equations of motion. You can ask how W++ evolves in under this stochastic fluid hydrodynamics, and you get, not surprisingly, you just get an ordinary Boltzmann type equation. Okay, let's look at it. So you have a streaming term of the Boltzmann equation with perhaps a non-trivial dispersion curve. I mean, you know, your omega q has this non-trivial dispersion curve, and it could be a function of space and distance. Okay, and then you just have looks like a relaxation time equation, which describes how the phase space density here evolves towards equilibrium. Okay, this is the classical equilibrium. So because we're doing hydrodynamics, we only get the T over omega part, or the soft small frequency part of the Bose-Einstein distribution. Okay, and in terms of this kinetic equation, you can write it down. You can look at this streaming term, and essentially it looks like a bunch of particles who stream with an effective 4D Hamiltonian, which is given in some kind of effective fluid metric. Okay, so if you take this fluid metric and you calculate how the momentum changes in time and the position changes in time, that describes how this pions, soft pions, will evolve in an expanding fluid whose velocity and temperature are changing in time. Okay, so it's very useful, this Boltzmann equation, and it will be very useful for doing phenomenology of the critical point moving forward. Okay, of course, once you have the Boltzmann equation for these modes, then it's like normal steps, traditional steps, to go from this Boltzmann equation to computing with known dispersion curve to computing the shear and bulk viscosities associated with this mode. Okay, so that's what we did. Okay, so using this Boltzmann equation, you go compute the shear and bulk viscosity following standard steps, and you get some expressions. For instance, the bulk viscosity has this traditional form here describing how the bulk modes relax. Okay, so now in this thing, you can now do this integral, and you get a result for the bulk viscosity, right? So the bulk viscosity is written here, and let's just say what all these parameters are. Okay, so first of all, we have what's the temperature derivative of the thermal velocity, which comes in this way, and the temperature derivative of the thermal mass, which comes in this way. Both of those functions are Euclidean. They're known. They're known from Euclidean QCD, right? Now, then the final result depends on the ratio of these two transport coefficients, which I kind of wrote here, and you get some relatively complicated expression, which we're going to have to try and tear apart a little bit. Okay, so here are the other ones. Okay, you have the shear, you have the bulk viscosity. This is the Pion contribution. You have the shear viscosity. This is the Pion contribution, and you have the bulk conductivity. This is the Pion contribution. Okay, so let's tear it apart a little bit. Okay, so of course, not surprisingly, it depends on the two transport parameters, one of which is the axial diffusion coefficient, dA, and the other of which, dm, is parameterized by this ratio r. Okay, and then it depends on the Pion mass, or the screening mass here, in ways I described at the beginning of the talk. So the bulk is proportional to the mass, the shear is proportional to the mass, and sigma is inversely proportional to the mass. Okay, so let me try and take these expressions and kind of approach the critical point. So I can't get too close to the critical point. I mean, so the order parameter is, psi bar psi, and it generally has an amplitude and a phase. And we're only including here fluctuations of the phase, whereas in general, you would also need to include fluctuations in the amplitude in order to describe the O4 critical point. And I won't include the amplitude here, but you can see the next talk, okay? And let's just talk about the phase. Okay. Okay, so here's our results, a little more simplified near the critical point. Now, this first terms are all given by static universality, so we know how they depend on the critical point. Now we need to address how does this depend on near the critical point, this dynamic transport parameter, okay? And that's also known. So near TC, the Pion relaxation rate should be the same as the order parameter because the Pion and the sigma are both the order parameter together, okay? And so the Pion damping rate, which is dA times q squared, right, is given by dynamic universality, and it should scale like the correlation length to the power z, where z is a known dynamical critical exponent, which turns out to just be d over 2, right? And so with known behavior of the correlation length near the critical point, you can find that the behavior of dA near the critical point. And that gives you then basic predictions for how these three quantities should scale near the critical point. And here's sort of, say, our results here. The bulk viscosity is some bare bulk viscosity, and then you have a piece that's coming from the Pion contribution. And we have a known dependence on quark mass and known critical exponent. And so we basically find that the bulk viscosity should decrease sharply near the critical point with a known power, the minus 1.81. The shear viscosity has a positive exponent here, and it should grow slowly near 0.019, okay? And finally, in the Pion contribution, this sigma, it has the Pion contribution dominates the result because it goes like 1 over square root of mq, and it should basically fall like a t0 to the 0.55 with some known powers. So now we've done, let me kind of give some, this is sort of our results. Okay, so bulk decreases sharply, eta grows slowly, and sigma falls as specific power. The next talk will show this over the full range. So let me just anticipate somehow the next talk a tiny bit. So this is outlook, see the next talk, right? So the conductivity near TC should have some regular piece, which we're not computing, and then some critical piece, which we are computing, at least in mean field approximation. And the full results somehow is this green curve for the critical expectation for how the conductivity should scale near TC, okay? And okay, and it does exactly what we sort of said. So if you look at just the Pion contribution, which is what we computed, you see that it basically tracks, Pion kinetics tracks the whole critical theory up until about TC, so right at the boundary of applicability. So it's kind of reasonable to use this Pion kinetic theory to describe, critical behavior up and kind of to the boundary of applicability. Okay. So of course, you might be interested in like, what are the absolute units on this scale, right? So I tried to estimate it here. So this absolute units is given by some constants, which are related to these temperature, the screening mass, and the diffusion, this diffusion constant, transport parameter. And so I tried to estimate it for physical parameters. So if you want to make an estimate for what the conductivity is, what you usually care about is the diffusion coefficient. So take this sigma and divide it by the susceptibility. So taking some reasonable parameters for the screening mass, the transport coefficient, okay, and this susceptibility, you get sort of one or approximately 1 times the bound. So this whole scale is like 2 times the bound. Okay, it's what you're talking about here. Okay, so that's the first outlook. So my second outlook would be, can you see any of these modifications of the pions at small momentum? And here's sort of outlook 2. Okay, so evidence for the chiral crossover in the heavy ion data. It's kind of speculative, right? That's why it has a question mark in the title. But if you look at ordinary hydrodynamic fits, which usually do very well, okay, they all have this nagging, or not, maybe not all, but most have this nagging problem with soft pions. Okay, so if you look at the yield of soft pions, they're always enhanced relative to kind of hydro fits, right? And it's all down here in the muck, right? So it's at a very small momenta here. Most experiments, I mean, for instance, CMS experiment doesn't even measure these, okay? So only ELISE really measure these very soft pions, okay? And usually there's sort of a striking enhancement here, which is difficult to explain. I mean, these codes, the traditional explanation is resonance decays. These codes all have them in, you know, hundreds of them, even way too many resonance decays, if you ask me. And still they miss, right? And it's a problem because the shape is what you're missing. So I think, okay, that this is because you're neglecting some physics associated with the pion dispersion curve down here at small momentum. So the pions are Goldstone modes. So you expect an enhancement at low PT. In particular, if I look at the Bose-Einstein distribution, right? It goes like 1 over the, you know, this thing, which is approximately T over VQ, right? And as we said, the pion velocity, like on kind of general grounds, right, is going to 0 near TC, right? And so you expect, since this is going to 0, that this yield will go to, you know, infinity. Now, in the real world, of course, you have a mass there, and because of that mass, it won't go to infinity. This won't go to 0 precisely, and you won't go to infinity precisely. But nevertheless, the basic trend would be that you should expect a small momentum and enhancement due to the fact that the dispersion curve of the pion has changed. That's due to the fact that pion is a Goldstone mode, and that Goldstone mode reflects the chiral transition. All right, so I am done. I haven't kept track of time. Let me come to my summary, okay? So, you know, here was the basic picture. We had hydrodynamics, right? And at shorter distances, we have these superfluid modes, and at still shorter distances, you have the particles, right? And so if you want to, we wrote down the appropriate SU2 left cross SU2 right superfluid theory, which describes these pion modes. And although I didn't really discuss it here, you know, we wrote it down in nonlinear form, and we included viscous and mass corrections, and in some sense analyzed entropy production, and in some sense that is what we did relative to Son and Stefanoff many years ago. Then we, following modern world, right, we analyzed the hydro equations, the stochastic hydro equations, and derived a kind of kinetic equation from those stochastic hydro equations. And, you know, this kinetic equation for soft pions has a with this very specific dispersion curve, can really be useful for phenomenology. I mean, I would like to sharpen up the statements I made on this previous slide, okay, using this transport equation for the soft pions, and see whether we can describe somehow the discrepancies in the data using this kinetic equation. So finally, we determined at a technical level how the ordinary transport coefficients of QCD depend on m pi, right? And as we said, it goes linearly in m pi, or like square root of the quark mass, okay? Good, and we did that. You can either do that by integrating out hydrodynamic loops and find the square root of m quark dependence, or by solving the kinetic equation, which is typically easier, and finding the dependence of the transport coefficients on the pion mass. So as you approach the critical point, right, you should develop an O4 scaling hydrodynamic theory in hydrodynamics, where the chiral condensate has this amplitude and a phase, right? And you should then include the fluctuations in the amplitude as well as the fluctuations that in the phase, okay? And I would say you should stick around for the next talk where we did exactly that. And nevertheless, even the Pion theory, as we showed, gives a pretty good description over a good portion of the range of the O4 critical point. Okay, thank you.
Thank you, Derek, for this beautiful talk. And of course, you will come to India. We will have an opportunity for that, surely. Okay, so I'm thinking that since the next question is, the next talk is connected to yours, I'm thinking that maybe we take only 2 questions now and then postpone all the other questions for after Alex's talk. Is that okay? Or you want to take all questions now?
Well, okay. I think we could take them all now, and then
we could have a discussion session now. I don't mind starting later as well.
Okay, so that's fine. Okay, then first question is by Soren.
Yeah, should I ask it myself? Okay. Yeah, hi Derek, first of all.
Hi, Soren.
So if I understood correctly, your analysis includes somehow the coupling between fluid and pion modes, but I didn't see somehow that you have essentially pion couplings between pions. Is there a reason that you can neglect them?
Good. So first of all, okay, so if good. So in general, you would have a nonlinear SU2 left cross SU2 right theory, and that would lead to, which we wrote down, and that would lead to pion couplings between scattering between each other.
Yeah.
No question. Now, if you have a mass, then the fluctuations in the phases are small, right? You can, yeah, because you're expanding around 0. And then, you could linearize the theory. Now, and final statement would be, of course, if you're talking about very soft momentum, the interactions between these modes, between the soft modes, is small, right? It would be then like loop corrections to the pion theory, right?
Right, but I mean, I would have thought that as the pion becomes light, these become very important, right?
I mean, as you go near the critical point, for sure. I mean,
Okay.
Yeah. In the limit that in the region where I used it, which is the region where I used it, you basically, which is the temperature should be close to the critical point, but still well below the critical point. Then you have a Gaussian theory for the pions.
Okay, I see. Okay.
And then it's valid, right? Of course, as you get near the critical point, then of course, eventually, in order to get the right critical exponents, you A, need the sigma, and B, you need the pi-pi interactions, and you need to simulate it.
Okay, wonderful. So this actually, may I ask my second question, which kind of directly follows up to what you just said, is
yes.
So if you actually consider this, I mean, if you actually consider QCD and you take the O4 critical point, right?
Yeah.
Is it actually known what's the dynamic universality class of that? Has that been firmly established? I
mean, as you know, right? You have these equations from Roger Gopal and Wilczek, right?
Right, but that's I mean, that's like a bosonic O4 model essentially.
Yeah,
so
it's kind of
bosonic. That doesn't include things like you are like coupling to the fluid sector.
Right.
Would that change anything? I mean,
so good question.
I mean, the other one is model G. This I know, but
my working assumption is is no, because the O4 static exponent for the energy momentum tensor alpha is negative, right? Which is the argument that Wilczek gave, right? However, as we'll see, we did a mean field calculation of the bulk viscosity, which Alex will describe next, right? And there we see that this loop corrections to the bulk viscosity are parametrically enhanced by the quark mass, right? Like 1 over with the known power. I don't have it off the top of my head, and so I would want to re-examine that because of this, and that there may be a region like where you can basically neglect it, but I think as you get very, very close to TC, I wonder if you need the coupling to the energy momentum tensor.
Okay, I see.
And
so your working assumption is it's model G basically, and
yes,
it could change in principle. Yeah.
And as you'll see, and there's even a parameter, right, that as Alex says, which is essentially it goes like this tilde the bulk viscosity goes like this tilde mass squared, and that has a very strong behavior near TC, and that would seem to me to suggest that maybe you need that sufficiently close to TC. It has a small amplitude, but it changing rapidly, that sufficiently close to TC, you might want to incorporate that bulk viscosity into the description, much like hydro plus plus is talking about.
Okay, I see.
There would be a regime like hydro plus where you could neglect it, but then there would, if you get like too close to the critical point, it would be some regime like hydro plus plus where you would then also need the energy momentum tensor. Good.
Okay, so the next question will be from Sayantan. Sayantan, would you like to ask yourself?
Yeah, hi Derek. So
Hi.
I was wondering if we approach if we are far away from the pseudo-critical point, then of course the pions are the dominant degrees of freedom, but then there are all these baryons which are banging against these pions. So how is it incorporated within this formalism? Or
I mean,
when we try to approach it.
Good. So I would, I of course took mu b equals 0 here, right? So this discussion was about mu b equals 0. Now, if you turn on a finite mu b, it doesn't change the dynamical critical exponents until you push the theory to the Z2 critical point, right? So at least for small range in mu b, everything I've done here is fine. It doesn't change the dynamical properties. It may change the parameters, okay? The parameters like dA and m, they all depend on temperature and UB, but it doesn't change the dependence, right? Because there's no Poisson bracket between the baryon number. You wouldn't need to include the Poisson bracket of the order parameter and the commutator of the order parameter, and the baryon number is 0, right, in the O4 theory. And so you wouldn't need to include the baryon number coupling as an explicit Poisson bracket in your hydrodynamic theory, and you would therefore just have the same hydrodynamic theory, but with parameters that depend on temperature and UB.
But even at mu b equal to 0, there may be baryons which
that's incorporated.
Which may affect
yeah, that's incorporated, right? I mean, that would be that's in the transport parameters. So of course, F, if I can go up, if I can go up, here. Of course, you know, the parameters of the hydrodynamic theories, such as F and M, right? They are temperature and dependent and mu b dependent, and that, and even at mu b equals 0, so the collisions of baryons with the soft pions and so forth, that's all incorporated into this T and M, right? T and M parts, right? And the baryon, the dissipative coefficients here, the sigma A and kappa zeta 2, right? Those are my two dissipative coefficients. They depend on temperature and in general mu b, and that would, you know, reflect the collisions of these soft baryons with these soft, sorry, the collision of the baryons with the soft pions.
Yeah, thanks.
I think the thing to keep in mind is these pions are so, I mean, the picture is the pions are so long wavelength, okay, that they don't just interact with any one baryon or any one row or anything else, right? They interact with the whole soup all at once.
Okay, okay.
Like the wavelength, the pion is much longer than the spacing between baryons, right?
Okay, okay.
Mm-hmm.
Thanks for this very nice talk.
Okay, so it seems there are no further questions from others. Okay, maybe I can ask a question. So Derek, it seems that you are not including the chemical potential dependence in the pressure, or maybe you're just including the mu square term to this susceptibility. What could be the effect if you actually take into account higher order corrections? I mean, we know the pressure has a very complicated dependence on the chemical potential, right?
You
And
like
that,
mu b or the
no.
axiochemical potential, or which chemical potential are you thinking of? The baryon.
The baryon one, or
Isospin one, for instance, right?
isospin, and yeah.
Yeah, so certainly if you turn on the isospin one, the theory becomes very, very rich, because then you become, and it hasn't been completely worked out. And it's a particularly fascinating, some of stuff was done by Son and Stefanov again at large isospin chemical potential. And it become, but in particular at large isospin chemical potential, one of the things that's extremely interesting is it really becomes then strongly non-abelian. And one of the things that I don't know the answer to is how this phase space, how this Boltzmann equation gets modified in the presence of a strong chemical potential, isospin chemical potential. And then it should become really non-abelian, much like, you know,
The Wong equation.
Much like the Wong equations, exactly. And I wasn't able to work that out, and unfortunately. I mean, I basically think I know, but it would be interesting to see that appear, these Wong equations at finite isospin chemical potential. And I must say, seeing this kinetic equation and at finite isospin chemical potential would be quite interesting from an ADS-CFT perspective, where the Wong terms would then show up as, like, you know, you would need somehow this non-abelian DBI actions in order to describe this or get this kinetic equations. So in that sense, it might be useful. Where I would be interested in seeing how first of all, what is the correct non-abelian generalization of this kinetic equation? And second of all, what is the gauge gravity correspondence to that in specific theories? Yeah.
But actually, can I ask another very basic question? So this chemical, if I just talk about the actual chemical potential dependence, it looks like you have only incorporated a quadratic term. So
Quadratic, right.
yeah, which means that you have only two derivative terms for the for the phase, for the Pion field. Suppose if I want to add, say, higher derivative corrections, and should the results be affected, or there's a way to check that they, or is it a way to understand higher derivative corrections?
I am not sure, actually. So if you say I have more mu hats running around.
Yeah, exactly. Mu hat to the power 4, for example. Yeah.
And of course, the mass tends to kill the mu hat, right? Because the mass basically, you have it's not conserved anymore. So the chemical potential is like decreasing in time because of the mass, right? So you're saying if I had some very strong mass, some very strong mu, which lived a long time, how would I modify the action? Yeah, it's a interesting question. I'm not sure I'm ready to answer that.